And then we are all set, and turn it over to you, Simon, for part 2 of matching and merging. Thank you.
Yeah, thanks a lot. So this will be the continuation of yesterday's lecture. And as I already announced, this will now focus on merging. So what I have been reminding you of how we distinguish matching and merging. Yesterday we extensively talked about matching to next to leading order. So this will give us essentially this box of fixed order calculation to improve the parton shower upon. And that means we get one additional jet at leading order, and we can describe the 0 additional jet bin at next to leading order. And what I will cover today is in fact how we start to sort of merge various jet multiplicities at leading order, such that we have at least a 3-level accurate result for hard multi-jet production for which the parton shower isn't reliable anymore. And then we'll have a go at how we continue that to next to leading order, and eventually see how that pushes us into an algorithm to combine with next to leading order. But that is just a combination. It's not a matching in the sense, and we'll see that explicitly how we discussed yesterday, the next to leading order matching. So that is the setting we're going to continue today. So this is, as I said, part 2 of what we'll do. So we'll start with leading order merging. We'll discuss next to leading order merging and the combination with NNLO. I have been thinking about whether I wanted to say something given outlook on shower development, but given also constraints on my side, I thought I would skip that, and it might actually turn out that today's lecture is not entirely covering the full hour. So apologies for this. But you can just ask me also by email or in private if you're interested in more material. So this will be part 2, as I said, for today. I should also say that if you look into the merging algorithms now, already by raising the word algorithm, you see that it's something which is very algorithmic, and of course we try to understand this in formulae, but given the complexity we want to address, right? We want to look into 0, 1, 2, 3, possibly more emissions and how they combine with the parton showers. These formulae become very technical and very unreadable. So I'll actually try and explain most of it by means of visualizing that logarithmic series and a few diagrams and event topologies and a few very sketchy formulae. So don't pin me down on each and every detail, but I hope this will get you the basic idea of how these algorithms work and where the pitfalls are. So let's have a go at leading order merging, and I wanted to remind you of what we've been discussing yesterday as well. We've been looking into what we call matrix element corrections. Now, matrix element corrections, if I look at this plane again, they would improve on the shower of the 0 jet configuration over here by adding in a first jet, and we would give a 3-level accurate description of this Z+1 jet, say, event over here. And merging is sort of the logical continuation of that, and is asking about what would happen if I would also have a 2-jet matrix element available and so on. And clearly now, if we don't just knock out the shower approximation to these 1 and 2 jet events entirely, well, we'll have an issue that we need to sort of slice up phase space in between regions which we feel should be populated by parton shower, and regions which should be populated by hard jet production. And then there's all kind of overlap going on which we need to deal with. And in the case of merging, we'll be at the leading order case, first of all, be doing that by considering different phase spaces, and the question of how we still maintain that we get an accurate resummation of multiple emissions by the parton shower. That is the main issue and the main art of doing merging, that we don't double count phase space regions, but equally well that we don't leave out phase space regions. And you might ask the question, okay, but if we can do matrix element corrections, why are we looking into these much more complicated algorithms in slicing up phase space? And essentially, the reason is boiling down that if we would do matrix element corrections, we would use the Parton-Schauer splitting kernel and then would replace it by something which is given by the ratios of matrix elements. Now, if n becomes large, that possibly becomes an efficiency issue, also in terms of phase space. But if you look closer in the literature and something which we haven't been discussing, if you have matrix elements which contain resonances, say you produce a TT bar pair and you look at the matrix element where you have the TT bar going to WWBB bar, then there's single and doubly resonant things in there, and depending on how you set things up, near or close to the resonance, your kinematics might steer this guy in a way that it will just explode, and then you need to sort of think about much more details of how you deal with that issue that is sometimes addressed by what people call resonance-aware matching, but in the end, it's a technical problem. We want to extract the leading behavior for soft and collinear radiation from that ratio that we know how to do, but it's not always feasible or desirable to place it back in full beauty. So one way or the other, we need to face some complexity here, and we need to solve that. So it's not all an easy and straightforward thing to do. And this is what I wanted to tell you about how we do this. So the name of the game is that we really, as I said, depicted here, we want to, in principle, for an arbitrary jet multiplicity, fill in these corrections at tree level. And we want to maintain things in a way that sort of we're not screwing up that feature that we get left over logarithmic contributions in our inclusive cross-section and sort of spoil the accuracy of the entire calculation, which is still starting from the lowest order leading order process. Now, the very first point to analyzing merging is simply to ask about how, if I would only want to improve things in the region of phase space which is available by the Parton-Schauer, what is the 1, 2, 3, 4, 5 emission state generated by the Parton-Schauer, and how can I improve on that? And so this is the starting point. And I've again sketched this here. Apologies, I've taken these formulae from an earlier lecture of mine. So what is called P in here, you should replace by the V from the lecture before. And it's the same, it's the splitting kernel of the Parton-Schauer. And now I'm being very schematic here. Otherwise, if I take into account all details, it will become very complicated. So what I'm asking is, as I look at this definition of how the shower acts on some observable, it will start at a hard scale Q0. And then the following might happen. It might decide to not generate an emission at all down to a shower cutoff mu. Then it might decide to perform one emission, but nothing up to that emission scale Q1. And now we have written down sort of something which is inclusive over all subsequent jet multiplicities. That's a very important concept in this context. Because we let the Parton-Schauer here freely act on that higher multiplicity. But still, it might decide that for this configuration with one emission, it would not go emit any further, and it will dress this up with the Sudakov factor for the n+1 Parton state, which is a product of the Sudakov factors for all of the individual branchings which could be going on and would lead to that n+1 or n+2 final state, and so on. And then we can iterate this formula once more, and then we get a 2 emission contribution, and so on. Now, this is already very suggestive of an algorithm that if we have knowledge of, like in the matrix element corrections, we had knowledge that this guy was approximating an exact tree-level matrix element. So why don't we just replace that by the exact cross-section? And I deliberately want to choose cross-section here because this will ease things when we talk about next to leading order, because clearly there's a one-to-one correspondence, as we've seen last time, between a tree-level matrix element and a leading order cross-section, but at next to leading order, that's not quite true anymore. So I prefer to talk about cross-sections rather than putting in matrix elements, but sometimes I use them interchangeably. And the same thing I want to do for the 2 emission contributions. So here's 2 splitting kernels, one of them describing an emission at a scale Q1, of the Born phase space point phi n, another one describing the emission of the point phi n plus 1, and then we go into and replace that by a 2-jet pre-level cross sections. And I want to do so only in a region where I do think that the matrix element is really needed. The parton shower isn't a good approximation to the matrix element anymore, and I'm able to calculate that matrix element. And I want to do this in here in a very simple-minded fashion, that I just identify the evolution scale of the parton shower being larger or smaller than some value at which I cut. And we'll see complications connected to the choice arise later on, and this will bring us again to the question of truncated showers, because in particular for an angular ordered shower, such a distinction would not distinct a hard jet emission from a softer one or a more collinear one, but it would do any weird thing. But we'll discuss this in a minute. But for the time, just assume that we have a distinction like this, and we'll make that a more precise criterion soon. So if I do this, then I would just look at these histories generated by the parton shower. So here's the double emission history. We start from some blob which describes the lowest order process at the Haar scale Q0. Then we have one Sudakov associated to an internal line here. Then we'll branch at this vertex. We'll go on. We'll have no emission probability for these two lines, and then we'll go on branching and so on. And this picture we'll use after having sort of wanting to replace this by the exact matrix element. We'll start to look at this exact matrix element and reinterpret it in terms of a parton shower history. And that is the starting point for most of the merging algorithms, for the very classic ones as put forward by Katani, Kraus, Kuhn, Weber, and then in a very efficient and transparent variant by Leif Lönnblad. We'll put in events for with hard cross section, exact hard cross section for no additional jet, for one additional jet, for two additional jets in here, and we'll start to interpret these as if they were created by the parton shower. So we'll use a kind of jet clustering algorithm. And that could be an operational jet cluster algorithm, or it could really be something which is sort of exactly corresponding to the inverse shower. Then we uncover this branching. So here we would directly see, okay, this is, well, there's nothing has happened. We just inclusive over what could have happened in here. And now we want to remove the overlap with further emission. So what we actually do is that we don't consider subsequent parton shower emissions in the matrix element region, but we really want to dress this up and make a statement that this has had no emission down to the separation scale rho. And so for the other one, I might cluster these two, and then I find a vertex and I get a parent parton, and again, I'm ending up with the hard process I start with. We can do that for the second one as well. And what we need to sort of take into account to make this more shower and more up to the levels of the properties which would the shower deliver to us, we need to take into account the running of alpha s at that vertex, which would be evaluated at the transverse momentum of the relative transverse momentum of this branching. And we'll need to account for these Sudakov form factors, which tell us that we want to have these up to the maximum multiplicity really being exclusive. So if this guy enters the game, we want to account for the probability that there was really no other jet and no other shower emission down to the scale rho as indicated by the Sudakov form factor. And then we're almost done. If in more complicated settings, if we would look at initial states, this is not a big conceptual change. We would need to account for the running of the PDFs, for the PDF ratio in the backward evolution. And then we could just think of now having generated an exclusive event sample in the matrix element region above this separation scale rho, and then we would start the parton shower at rho, if that makes sense for our parton shower. We would have obtained a consistent leading order merging. Now, there's various pitfalls in here, but let me first highlight an algorithmic thing. So the very first approach is essentially apply these Sudakov weights as numeric factors. in a certain approximation, but this turned out to have some issues if you look into the details. And the version proposed by Leif is actually working more closely to the parton shower and is using the properties of the veto algorithm to equally well implement these weights by essentially selecting these according to the no emission probability as it would have been generated by trial emissions in the shower. So I'm sure you've been hearing about the details of the veto algorithm earlier this week. So this would be the algorithm if the shower was all about just a single scale, and if we could have used that single scale to distinguish between hard and soft emissions. But that's not quite the case. It's certainly not the case for an angular ordered shower where large scales correspond to large angle soft emissions. But it might also not be true for any other combination, or one would actually just choose a different measure of separating the hard jets from shower emissions than one which is perfectly aligned with the parton shower evolution variable. And to highlight what's going on here, I've chosen to make that, to sort of sketch that difference in between these two measures by looking at the fictitious double variable phase space. It's not so fictitious, but it's just easy for illustration. So think about this as the phase space which is available to parameterize an emission. It's got two variables. It's got one variable which is referring to sort of a scale of hardness, and it's got another variable, say a momentum fraction. And in the case of what I'm assuming here is that the phase space which is available to the parton showers is the contours of fixed parton shower scale would be looking like these diagonals. So if I would start the shower at a scale Q0, it would then start to populate phase space down these lines. If I would start it at rho, it would start to populate phase space down here. And the measure I choose to sort of distinguish hard from soft shower emissions, I just identify by this horizontal line here, but just a simple scale thing. And then I could choose to sort of populate parton shower phase space over here, populate matrix element phase space down here. And now you already see one feature is which we've been not discussing in great detail when we were talking about interpreting the hard matrix element as a parton shower configuration. There might be phase space which is accessible to the matrix element, but not accessible to the parton shower. And so these we would then in the merging process sort of need add as a separate additional hard process, since these would not have been able to be produced by the parton shower at all. And this is also a very important detail when we later come to discuss unitarized merging. So that's my illustration of what's going on. And then I have that phase space, I have that for the first emission, and I have it for the second emission, I have it for the third emission. I don't want to necessarily order them in hardness to really make the point what's going on. So let's have a look. So suppose we have a first emission which we might be getting from the matrix element, and then we want to start the parton shower. Now we're supposed to veto the parton shower in the region which we would have assigned to the matrix element. So everything above that solid horizontal line belongs to the matrix element. We veto shower emissions in there, and then effectively we would then populate shower emissions below this line here. And then you can see another feature is that if we would start, as in that naive context I've been showing before, naively start the parton shower at rho, then we will produce a region which is not populated at all. So this already means that that we cannot just start the parton shower at this scale, but we need to start it at the scale it maximally has available, and then we need to veto emissions in the matrix element regions, and then we can freely let it go anywhere outside And so we will be populating this region because there's no veto in there. So say we had generated such a first emission, then the ordering of the parton shower tells us that the second emission must be below this line here. And again, something happens that, well, we might still be able again to emit into the matrix element phase space, so we would veto this. So everything looks fine, but again, there's a problem that there might be phase space which is left out. And to see this, just consider what we could reach maximally by making this first emission maximally hard in scale, so just at the boundary of the matrix element region. And then we would have a picture like this. So even if we have the maximal phase space available for the second emission, which we still would veto in the matrix element region over here, we could not possibly be populating this corner of phase space. And we're back to the original problem that the art of merging is not only not to double count phase space, but also not to leave out phase space. Now, avoiding double counting in this context is easy. It is vetoing in the different region, but as you can see, the real complication is about avoiding producing holes in phase space. So what could we do about this? Now, this is exactly one of the features we hit if the parton shower ordering is not the same resolution criterion on emissions than what we chose to divide the phase space between hard and soft emissions. And this necessitates truncated vetoed showers, which I've depicted here in green. So what we actually need to do is that we need to sort of bump up the starting scale of the shower to a higher value. And then we need to veto, of course, again in the matrix element region. And then we need to insert emissions which would have appeared to come before this would-be first emission in the evolution of the parton shower. And this is a truncated vetoed shower, and this is the important tool for, let me zoom out, sorry, why did it zoom in? For the merging, and actually has also been discovered mainly for angular ordered showers in the first place, but also later on for other settings. So we've solved the problem essentially at the boundary of the emissions to the hard phase space, and then we might convince ourselves, oops, what happens? Yes, this is what I wanted to talk about. So this is again the truncated showers. And as I said, in the context of merging, they have been looked at for the angular ordered evolution in Herwig, where the issue is really pressing, because here you can see what happens in an angular ordering, that there might be a hardest emission. Now this hardest emission and this hardest emission we would have wanted to replace by the 3-level 2-jet matrix element. But then if we would just naively do the vetoed shower business, we would miss out on these large angle softer emissions. And this is exactly what we put back by applying the truncated shower. And then once we have fixed up this issue, we can let the shower go on just as it would have done before. And this is on the last slide. So say we then have generated an emission below at such a low scale that we're free of any of these troubles. We can just let the normal showering go. So this is in a nutshell explaining how the problem with the vetoed and truncated showers and the different resolution works. And this is one of the very core problems you need to solve when talking about merging and when trying to design a merging algorithm. And this will be the feature which makes up a consistent algorithm. And one of the observables one typically looks at is the transition rate n+1 in terms of some jet algorithm, where we make a transition between an n+1 jet and the n-jet configuration. So this is the variable which you would assume is sort of sensitive to that boundary in between different jet multiplicities and the parton shower itself. And if the merging works well, this looks like, this just looks like a smooth curve, and at the scale which would correspond to row, you shall not be seeing any artifacts of the matching. And this is what we typically use. We vary that merging scale, and we watch out for artifacts of the merging scale in distributions of this kind. And for example, in the Herwig angular order shower, I've missed to put that plot, but it was there before in an older lecture, is that you would really see a massive step in here if you would just leave out the truncated shower. So these truncated showers, they are not only about, and this is not just a theoretical or formal worry, they are really at the heart of making up a consistent merging. So let's have a look at a bit more details of what we produce by these merging algorithms. And this is a development which has been driven a few years after these first merging algorithms came available, and was mainly triggered by trying to push the thing to next to leading order. But let's not go on so quickly. Let's just have a look what happens at leading order and ask, how is it different now from what we would have done with just the shower? And specifically, I want to ask about inclusive and exclusive jet cross sections. So exclusive jet cross sections, meaning that I require to have exactly n jets in that resolution criterion, which is given by my Parton shower set. So let's forget about the complications of truncated showering for a minute. Then asking for this exclusive jet cross section, I can simply write that down in a probabilistic manner from the Parton shower. It's my cross section by which I start with 0 additional jets, and then it's just multiplied by a bunch of splitting functions which describe how I generated n emissions of it, and then I need to weight it by a product of Sudakov form factors, which tell me that there was no more emission down to exactly that scale row. And here this notation just implies that we have a product of a Sudakov form factor going from Q0 to Q1, going from Q1 to Q2, and so on. Now, here, as I said, I've explicitly multiplied in the probability that there was no further radiation between Qn and rho. I could have just left that out and just multiplied by the Sudakov form factor, which goes down to the scale where the last emission happened. And in this case, I'm calculating an inclusive cross-section because I'm not asking what the shower has been doing afterwards. So it might have decided not to radiate anymore, then I would have gotten that last factor on top, or it might have just radiated anything softer down the evolution. And if we've properly set up the merging, then what we would have avoided is holes and notably double counting, and we would have replaced exactly and only this expression by the exact tree-level cross-section. If we had asked for an exclusive cross-section in the matrix element region. So in a sense, and we'll use that as a definition of a merging condition, what we have solved is exactly the demand that we want to have exclusive n-jet cross-sections in the merging region, not being screwed over by the Parton showering which happens around it. Up to the highest multiplicity where, of course, we can possibly or wish to possibly calculate the hard cross-sections. Now, asking for the inclusive cross-section, we'll actually see the effect of solving our merging condition, because in the inclusive cross-section, we of course have done the same replacement. So it's in one-to-one correspondence to this, but it can't quite be that, because we have jiggled around with the Parton shower splitting kernels, and it won't maintain unitarity anymore, because we have been replacing the real emission, the green bit here, by this cross section, but we've not been changing anything in the Sudakov form factor. So we've not been doing just a matrix element correction where this would have integrated to 1 in total. And the effect of this you can see here. So the bit which facilitated that we replaced the approximate with the exact matrix element, and which is accounting for that we don't get a unitary result back is, not surprisingly, the difference between the n+1 jet cross-section and the n part 1 cross-section dressed up, multiplied with a splitting function, and weighted by this combination of Sudakov form factors. So this is literally telling you that in the jet multiplicity higher, we have been knocking out this approximate guy in favor of the full guy, and then this iterates. Now let's have a look at this term in a bit more detail. And this term is actually, if you write it down diagrammatically, thinking about not these being Feynman diagrams, but just representing cross-sections, this is a tree-level n+1 cross-section. And this is a tree-level n jet cross-section multiplied by a splitting. Now, the region where we would get a logarithmic enhancement from this difference is, of course, the region where the shower would be a good approximation, so we don't expect any issue in here. And in fact, in inclusive cross-section, if the leading order merging works consistently, we'll not find any leftover logarithmic trace of our merging scale. That is another criterion for working merging. But we're happy to accept some change in normalization of these jet bins, which we can't control because obviously we're not doing neither a next to leading order calculation nor next to leading order calculation. So this will change, but the big gain we have is that we describe shapes of the different cross sections in the right way. And so this is what matters for a lot of observables. So the upshot is that if we do this at leading order, the message is this is not a problem. We can actually convince ourselves that this is not screwing over anything. And now we can ask about what would we do at next to leading order. I wanted to remind you what we've been solving for the next to leading order matching. So we demanded that the shower acting on the matched next to leading order cross section is giving us back the next to leading order plus higher orders. And that we maintain, and this is a crucial difference now to merging or applying a matrix element correction, that we maintain the next to leading order cross-section as the total normalization of what our simulation produces. And that we've seen we could be producing by using the NNLO cross-section by subtracting the order alpha S expansion of the parton shower acting on the leading order, and then this would satisfy our criteria here. And the parton shower is unitary also at any fixed order, so integrating over this term will just give 0, and we've satisfied the second requirement. For the leading order merging, we've solved a merging condition. The merging condition was demanding that we preserve exclusive cross-sections in the matrix element region and dress them up with the proper Sudakov factor, which tells us that this was an exclusive cross-section. So the demand was that if we act on however we set up our merged cross-section and merging algorithm, that if we acted a properly vetoed and truncated shower on it, that the n-jet cross-section at a resolution rho would exactly have that form. And now we want to ask ourselves, how can we combine them and make this even better in a way that we produce the next to leading order cross-section for this n-jet configuration. Now it's clear that talking about this, I don't have a one-to-one correspondence between a n-parton matrix element and an n-jet cross-section. So the NNLO cross-section, which we need to define here, will need to include a resolution criterion, which we actually can pick to be that jet resolution here itself, such that we can talk about an exclusive next to leading order cross-section by which we want to replace this exclusive leading order cross-section. And that is the starting point to define next to leading order merging. So we demand that next to leading order merging will preserve exclusive cross-sections in the matrix element region up to next to leading order. So if we act the parton shower within such an NNLO merging calculation, we would want that this pattern here is produced, where this guy here then becomes the next to leading order exclusive cross-section for n jets at these resolutions plus order alpha, relative order alpha s squared. There's variants of the merging algorithms which are going beyond that and which also sort of try to preserve the entire cross-section, the differential cross-section in the shower region up to NNLO, but this is a minor distinction. The main thing is that we want to have this exclusive cross-section being bumped up from leading order to a next to leading order exclusive jet cross-section and achieve to fill in this dot which we had access to before by the next to leading order matching, and then of course also the next to leading order corrections for the first additional jet. And again, we need to ask ourselves about what would happen in the inclusive way. Now, if things work in the right way, then surely what we should be observing is that we get the next to leading order cross section back. But then there's a problem appearing in the second jet multiplicity, and this is something which one then needs to worry about. And this is again connected to what we've been looking at before, the question about exclusive and inclusive next to leading order cross sections. And as I said, by construction, what we get out now from a next to leading order merging is that we have now this guy here available as an exclusive NLO cross section. So this is really this is missing the word exclusive. This is the exclusive NLO cross section for n jets. And then at inclusive higher jet multiplicities, we can again ask what would have happened. And then something funny happens. And the correction term we've been looking at before now again has the same form, but now this guy here represents an NLO cross-section for n+1 jets. And this guy represents an NLO cross-section for n+1 jets multiplied by a leading order splitting function, which is coming out of our leading order Parton shower. And that could be a potential problem, because obviously the leading order Parton shower isn't a good approximation to the full NLO cross-section for n+1 jet. So we really need to look at this guy in more detail, because this might end at a parametric order which is of the same at the same level of the NLO correction which we want to include for n-1 jets, and that's certainly not something which we want to screw up. And that is, removing this issue is at the heart of what we call now unitarized merging algorithm. And this I wanted to talk about, at least in a bit of a sketchy way, in the next few slides, and show you how this enables us to make contact with next to leading order and possibly even higher. But already what this highlights here is that if we want to enter the game of sticking together two NLO calculations, so something which is a subset of a full next to leading order calculation, we're probing a regime which tells us that our Parton showers aren't good enough. But in this case, it still works. And it works in the following way, that if we look again at this graph here, which reflects the different contributions. Now, what I can do is that these spurious things which would have been appearing here due to this difference here, that I can actually remove them. I subtract them in a way that, so I construct my merging algorithm in a way that I really reproduce the proper inclusive cross-section over here. So I'm changing my merging condition, that I'm accepting a change in my exclusive cross-section. And you can convince yourself, if you look into the details, that that change is not worry. But I actually demand that I preserve inclusive cross-sections, or at least inclusive cross-sections in a region where there's a logarithmic enhancement. So I guess in the first attempts of unitarization, if you really strictly subtract everything of that kind, you could be getting quite some unphysical cross-sections at low merging scales. But if you organize it in a way that you only remove those which would be logarithmically enhanced, and there's a one-to-one correspondence to whether the could have been produced by the parton shower or not. Then things worked out. And so what we've been doing then is that we've generated something which is now sitting as a contribution in that zero chat bin here, and which is formally of an approximate next to leading order contribution. And something similar would have happened if we would have played the unitarization at leading order. So we could have looked at leading order, and we could have merged leading order. We could have been observing the possibly problematic term. We could have unitarized it away. And by unitarizing it away, we produced approximate next to leading order calculation. I've used this little n to highlight an approximate contribution here, and this is a reference which is actually missing. This is the same notation then which has been used by the loop sim method, and in fact the whole procedure is inspired by this algorithm, which is sort of doing unitarization at the level of just a fixed order calculation. And then we could have said, well, hey, there's approximate next to leading order, but I know about the exact next to leading order. I can calculate a next to leading order exclusive cross-check section. I can stick that in place of this approximate one. And this is what I call combining rather than matching, because matching is really not appropriate. But what we have achieved by this is that we now can merge next to leading order. Now the same would have been accessible by matching, but not and which is the much more flexible way, by the way, and which is less prone to ambiguities we have in this merging scheme. But okay, let's continue this pattern of moving here. So now we have seen this. We again identify the problematic guy. We subtract it away. We generate approximate next to leading order contribution through this. And again, you could say, but hang on, I've got the exact next to leading order exclusive cross section for Trevelyan plus zero jet, say, at a certain resolution, and then I again can play that game, and I can replace these contributions here by what I know exactly by running next to leading order calculation for Trevelyan. And this was the first sort of application of combining using unitarized merging with to sort of combine with next to leading order. And a very similar consideration, though, with a much more analytic insight is behind the NNLO methods. But in the end, they follow a completely similar paradigm. So again, if we want to really improve on this for the first two check multiplicities, and we would want to match to next to leading order in the same way we matched to next to leading order, that is only possible if we get better parton showers, which are really then suited for including any doubly unresolved limits, which we would need to conquer the divergences we see in next to leading order calculation. So recall that the expansion of the shower we used in matching, that was just about sufficient to cancel the divergences we have been facing in the next to leading order calculation. So if we want to play that game, we need to work on our showers. So this is the last thing I wanted to tell you in the context of merging. But as I said, it's not that big of a problem if we think about that we generate this from merging next to leading order calculations. But these calculations are not as flexible as a full matching would be. To finish off this lecture of today, let me show one particularly neat example, actually a more recent one. So there's plenty of applications of NNLO multi-chat merging leading order and NNLO and next to leading order multi-chat merging. I just wanted to pick this example, which is a very traditional process. It's just Trevelyan plus chats, where sort of several of the hadron collider merging algorithms have been benchmarked. And this is particularly amazing because this shows you how the method actually goes up to including up to a 9-chat matrix element. So this is a computationally extremely efficient thing. But here you can see these variables which have been mentioned before. Here is the transition from a W+1 chat event to a W+0 chat event. And this is nicely stable, and you can see how it's composed out of the the zero chat matrix element at low resolution, and then the zero chat matrix element is dying off. And then the one chat matrix element kicks in, fills in the tail, but the tail is made up of larger and larger chat multiplicities as well. And equally well, you can look at the 9 to 8 transition scale, and there is no bump, nothing at wherever the merging scale was in this case. So this is really working, and also as next to leading order matching, leading order and next to leading order multi-chat merging is really established technology. You should be aware that in merging algorithms, there's much more ambiguities involved than the ones we have been highlighting for the next to leading order matching, because we need to decide on how we reinterpret hard matrix elements in terms of shower histories, where we draw a line between what we think the shower could have produced and what we think the shower could not have produced. How we select different histories among each other, and whether we apply unitarization or not. But the big advantage of unitarization is really that we sort of iteratively and systematically control and produce approximate higher order corrections, which you can then replace by exact ones once they become available. And this you can also see in the development of the current state of the art of multi-chat multi-purpose event generators, which of course can describe multi-chat physics. So all of them have facilities to perform multi-chat merging at next to leading order, and all of them also now offer unitarized merging, which I think was first proposed for Pythia and Herwig 7, and then first implemented for Pythia, and then later on for Herwig 7 with some improvements. So I think these tools are really helping us to do a lot of rock solid phenomenology with multi-chat final states. And of course, this is not the end of the story, because we do want to advance our technology to make full use of next to leading order, currently only with the unitarized methods available, but hopefully at some point also with a fully differential and flexible matching algorithm. And this brings me to the end of this second part of this lecture. I wanted to thank you for your attention, and if there's any questions, please ask.
Okay, we have time for a few questions. If there, let's see, let me check the chat. Okay. Anything pressing?
Otherwise, I will make an effort that last night it was not possible for me for private reasons, but I will try to be available tonight, but I can't guarantee that yet. But I'll make an effort to.
Okay, very good. So yes, so I don't see anything at the moment. So if there are no questions, again, collect up your questions for this evening. There are recitation exercises that are posted under the recitation part, and we will discuss those or anything else you'd like to, and also bring any questions you have about the tutorials, because this will be your last chance if you want to do something over the weekend. And so we will see everyone at 2000 in Gathertown. So very good. Simon, thank you again, and have a good afternoon or evening. Take care.
Okay. Thank you.
Okay.
Bye. Bye.
Bye now.
Thanks.